So, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. These are the words of Niels Bohr, one of the founding fathers of quantum mechanics, who we see here in this picture together with Albert Einstein, of course. And actually, for Einstein himself, quantum mechanics was so profoundly shocking that he really had a hard time even just accepting this new theory of quantum mechanics, even though he was also one of the founding fathers of this new theory. But shocking as it is, we now know that quantum mechanics is the most precise theory of nature ever invented. So one of the more interesting questions which were asked in the last couple of decades was, can we use this? Can we make advantage of this new quantum world? And can we make it work for us? And more precisely, can we build computers that are based on this new theory of quantum mechanics? And can they perform any better than our regular computers, so-called classical computers? So you might have heard about quantum computing. It's been in the news quite often recently with many of the tech giants like IBM and Google introducing their latest developments in the field, the latest quantum processors, quantum cloud platforms. They're actually quantum computers on the cloud that you can access and run actual quantum algorithms on. These are still very small prototypes, but we can actually do that, so this is very cool. And you might have heard about this term, the race for quantum supremacy. So quantum supremacy would be the first demonstration that a real quantum computer, an actual quantum computer, can perform some tasks faster than any other classical computer that we have on Earth. So this is actually expected to happen this year. This is not going to be a useful task yet. It's just going to be kind of like a proof of concept that quantum computers can do that. But this is expected to happen this year, so it's quite exciting. So we see that quantum computing is generating a lot of buzz, a lot of news. And the reason, of course, why it's so interesting to so many people and so many companies is this great promise for great computational power that these computers are expected to offer us. So this is a relatively short talk, so I won't have time to go into many of the aspects of quantum computers, like how do we build a quantum computer and what are the main challenges and where exactly we're at today. Because what I want to do is I want to focus on really try to give you an intuition about how these computers work. What is the difference, what is the main fundamental difference between quantum computers and classical computers, and focus on what in this fundamental difference allows quantum computers to be more efficient in some information processing, some calculations. Okay, so I hope that with this sort of like basic introduction, you would be able to go on and read about the field and in a more knowledgeable way and learn how it might be relevant to you and so on. Okay, so before we talk about quantum computers, we need to remind ourselves a little bit about how classical computers work. Classical computers basically on a fundamental level have two building blocks, one is the bits, of course, which is how we store information on the classical computer. Okay, so a bit is simply a system that has two different states. We usually call them 0 and 1. This strange notation here is just how physicists denote states. Okay, and this is how we store information on the computer. We have actually many different ways to implement bits on the computer. For example, we have many tiny electrical wires in the computer, and each wire can be either on 0 volts or at 5 volts. And this is how we physically implement a bit on a computer. There are many other ways to implement bits. So we can take many bits and we can store a lot of information on a modern computer. But then we need a way to process this information. This is a second building block, which are the gates. Okay, so gates are these devices that take in some input bits, perform some function on them, and then gives us back some output bits, the result of this function. So this is the NAND gate, for example. This is the function that it does. And the NAND gate is actually an example for a universal gate, okay? Which means that using only NAND gates, we can perform any function, any manipulation, any processing on any number of classical bits. Okay, which means that we can take a bunch of classical bits and we can start manipulating them, which means we make them go from one state to another and to another at every point in time, according to how we wire these gate operations. And this is on a kind of an abstract level, this is a computer, a classical computer. It's this machine that has many, many different states, and it just goes from one state to another and to another according to this gate program, okay? Until it reaches some final state, which is the result of the program, the result of some meaningful calculation. All right, now quantum computers replace this notion of a bit, the classical bit, with the notion of a quantum bit, or in short, a qubit. Okay, so while the classical bit is restricted to being either 0 or 1 at every point in time, the quantum bit, the qubit, can be in both 0 and 1 at the same time, okay? So we call it the superposition principle, right? It's kind of like the Schrödinger cat being both dead and alive at the same time. So we don't know yet how to do it with real cats, but we can do it with small particles like electrons, for example. We can make electrons be in for example, two different positions, or two different states. So we can make qubits in reality, and they are in these superpositions. They're both 0 and 1. But in fact, it's not that they're just both 0 and 1. Really, they can be in any combination of 0 and 1. Okay, we write it like this: alpha 0 times the 0 state plus alpha 1 times the 1 state. And these alphas, these coefficients of these superposition states, are called the amplitudes. Okay, and these amplitudes, they kind of tell us how much the qubit is 0 and how much it's 1. Okay, we can be a little bit in 0, a lot in 1, or vice versa. But in fact, it's even a little bit more complicated than this. And this is really kind of the heart of quantum mechanics. These coefficients, alpha and beta, these amplitudes, are really complex numbers, okay? So it's just one of those things that we have to accept. This is how quantum mechanics work, and we'll see how this becomes very important for quantum computing. So these coefficients, they're not just magnitudes, not just how much I'm in 0 or 1, but they also have phase, right? They have a direction. So I can be in half 0 and minus half 1, okay? All right, now there is a way to write these superposition states in a simple way in terms of vectors, okay? So this superposition would be just this two-dimensional complex vector, and then there is this rule that says that the norm of this vector, these vectors must be normalized, okay? And this is basically the rules of quantum mechanics. This is really the heart of quantum mechanics. There is another way to look at these, visualize these qubits in terms of a vector on a sphere. So you can think about a three-dimensional sphere, and then the qubit can point in any direction on the surface of the sphere. Okay, so then you can see that this is really just a generalization of the bit. So while the bit is restricted to 0, 1, right, just south pole or north pole, or one of these two basis vectors, 1, 0, 0, 1, the qubit can be in this linear combination of these two basis vectors, again, with complex coefficients. Okay, so then this is really like, there's not much more to quantum mechanics than this. This is really the heart of the matter. And just like in classical computing, we had gates to process classical information, so in quantum computing we have quantum gates to process quantum information, to manipulate qubits. Okay, so this is a single qubit gate. It takes a single qubit and manipulate it. So this means that it performs some transformation on this vector, right? It takes the qubit from one state, one vector, to another state. So these transformations, these gates, are described by unitary matrices. So unitary matrices are just matrices that preserve the norm of the vector. So I told you that the norm has to be 1, so unitary matrices just preserve the norm. These two vectors must be normalized. So this is an example for the Hadamard gate. It's a very famous gate in quantum computing, and this is the matrix that represents it. So each qubit is described by this vector, and when we operate on the qubit, we operate with this matrix. Now we also have two qubit gates. So a system of two qubits would be described by a four-dimensional vector. Okay, why is this? Because you can think about a system of 2 bits, right? It has 4 different states, 0, 0, 0, 1, 1, 0, and 1, 1. So a system of 2 qubits can be in a superposition of all of these 4 states, right? Both 0, 0, 0, 1, 1, 0, and 1, 1 with with the corresponding amplitudes. So we describe this by a 4-dimensional vector. And just think about the fact that this vector grows very, very quickly with the number of qubits, right? Because the number of classical states that we have, if we have n qubits, is 2 to the n. So a system of n qubits would be able to be in all of these 2 to the n states at the same time. So the size of this vector goes like 2 to the number of qubits, okay? So for a very small quantum system of only 300 qubits, you would need an amount of classical information. You need a number of amplitudes which is larger than the number of atoms in the universe. Okay, so a small quantum system can really hold a lot of classical information. Now, so 2-qubit gates would be described by 4x4 matrices, again, unitary matrices. This is the C0 gate. It's another famous gate in quantum computing. And now, just like we had in classical computers, the notion of this universal gate, right? This NAND gate that which we could, perform only with NAND gates all the different computations. So in quantum computers, we have the same notion of a universal set of gates, which means that only with 3 single qubit gates and 1 2-qubit gate, the C0 that I just showed you, we can perform any manipulation on any gigantic vector like this, any system of any number of qubits, and transform it to any other state, okay? And this is basically, and so we can basically create a general quantum computer, which is basically this system that has many qubits, and it just goes from one superposition of states to another superposition of states to another superposition of states at every point in time, according to the quantum gates program, okay? According to how we decide to operate with these unitary matrices. And this is a nice picture, right? Because it shows this very big sort of fundamental difference between the classical computer and the quantum computer. While the classical computer can sort of only go in one of these paths, one of these computational paths, the quantum computer can really go in all of the different computational paths at the same time. Okay? All right, so then there's an exponential number of such computational paths. So this is really powerful, but most popular talks about quantum computing pretty much end right here with this picture saying that quantum computers could do parallel computations with exponentially faster than classical computers. But there is a big problem with this picture, okay? And you can kind of see it already from here. And this is the fact that at the end of the calculation, we also end up with all the different results in parallel, right? A superposition of all the results, okay? And this is not really what we wanted, right? We wanted a single answer, the right answer. And this gets even worse because there's another important thing in quantum mechanics that says that when we look at the computer, when we want to get some result from the computer, we measure the computer and we can only get access to a single state. This is called the wave function collapse. This means that when we look at the computer, we never see the superposition. We just sample from this sort of distribution that's given by the amplitudes of the state. And we don't even have a way in advance to know which answer we're going to get. Yeah, it's going to be different every time we run the same program. So it doesn't look too good for quantum computers. But there's a way around this, okay? And this really goes into the heart of how quantum computers work and why they're really can get advantage over classical computers. And it goes something like this. You see, if we look at the quantum algorithm as this series of unitary matrix operation, where we go from one superposition to another, going in all these different paths, each different computational path is going to, at the end of the process, going to be assigned some complex number. For example, this red path over here is going to be assigned this gamma alpha term. And this other red path over here, which leads to the same computational results, is assigned a different complex number. Now, because these are complex numbers, because they have these phases, they have a magnitude and a direction, they can cancel each other out. Okay, so these two red paths leading to the same computational result can cancel one another and give us, for example, a 0 amplitude for this state, while the other two red paths leading to the other computational result can add together, can amplify one another and give us, for example, a high probability to measure the state. Okay, so this effect is called interference, that different paths can either interfere constructively or destructively, cancel each other out or amplify one another. And this is really our only way to make parallel quantum paths, work together in sort of a collaboration and cancel out the wrong results to the problem and amplify the correct result to the problem. Okay? This interference is also the only way we can see quantum mechanics. So this is the only way we can really see that the true nature of physics is quantum mechanical. So this is also how we can leverage this, by designing the interference. So you see, the interference is really this magic fuel that kind of fuels quantum computers and allows them in some situations to perform faster than classical computers by taking the advantage of this parallelism. But it's not like we can just try all the different paths at the same time and expect to get something better than classical computer. We need to design the interference to and take advantage of the structure of the problem so that the wrong results to the problem cancel out and we only get the right result. So really, like, designing quantum algorithms is sort of an art. It's very hard to say in which problems and what kind of problems quantum computers could be better at. But we have examples. We have examples like the Shor's algorithm. So this is how the Shor's algorithm looks like in terms of gates. And this is a famous example where we can break down large numbers into their prime factors, which is basically the problem that stands behind the RSA encryption, right? So a large-scale quantum computer, which we're, by the way, very far away from, would be able to crack RSA pretty easily. Again, by exploiting the quantum Fourier transform, basically exploiting interference. Okay, so now in the last 8 minutes or so that I have left, I was asked for this talk to relate quantum computing to neural networks. And there are a couple of interesting connections, possible connections, that I want to talk about, and again, without going into too much details, kind of just give a little bit of the intuition of why we believe there is an interesting connection between the two. Okay, so the first kind of connection is quantum computers for neural networks. So this would be using quantum computers to improve neural networks, okay? So again, to give an intuition for this, why we think this could have a potential, again, everything that I say from now on is not really proven yet. People are working on all of these things, but there is no proof yet that these kind of quantum algorithms will give an advantage for these things that I'm going to mention. But it's a very active field. So one of the ways to visualize these quantum algorithms in a sort of a different, from a different angle is called adiabatic quantum computing, where we basically design a potential landscape for these qubits to be in, okay? And the qubits will always look for the lowest energy state on this potential landscape. Now, you can think about this potential landscape as being the cost function that we want to minimize. Now, we can start from some potential landscape where we know the solution, we know where the qubits will sit, and then we can change the potential towards the cost function that we're actually trying to solve for. So classically, when we change the potential, the ball will remain in the left valley, right? And it will get stuck in the local minima. But quantumly, as we change the potential, when the two valleys are at the same potential levels, the qubit will actually go into a superposition. This is kind of as performing the Hadamard gate that I told you about earlier on the qubit. These Hadamard gates make qubits go into in superpositions. And then as we continue to change the potential, the qubit will choose to go to the lower energy state. So this way of looking at the quantum algorithms give us sort of an intuition why we think that perhaps there is an advantage for quantum computers in solving some of these difficult optimization problems, and people are working on that. All right, now you can think about, having, like the quantum system being in all the different parameters of the network and trying to find, the right parameters. But this is kind of far away from where we're at with actual quantum computers and, given, the interesting neural networks. So people have tried to take a more kind of a modest approach lately. This is called quantum classical hybrid calculations. And this is basically to break down this solving of optimization problems to two parts. One, to compute the cost function, and this is done by the quantum processor if it's a cost function which is hard to compute. And then for given parameters. And then the classical computer does the variations on this parameter space, okay? And people and people believe that these will actually be the first kind of applications for quantum computers. Okay, so this is called quantum classical hybrid algorithms. So the quantum computer does some of the calculation, and then the classical computer does some of the calculation, updates the parameters, and then we run again the quantum part of the computation. And then you can also think about, fully kind of quantum neural networks, where the network is basically in a superposition of different neural networks, right? And so you can think about neurons that can fire and not fire, and this has been a subject for research in very recent years. And people believe that perhaps we will be able, by exploiting these superpositions and interference, identify certain patterns in the data, again, by taking advantage of interference. All right, now lastly, this is, I think, the most relevant kind of connection between neural networks and quantum computing for the near future. And this is actually neural networks for quantum computing, okay? We're trying to build these very, very complicated machines, these quantum computers, and it's a very challenging task, and we're pretty much exploiting all of the different technologies that we have, so it just makes sense to use, neural networks. But to give you an intuition why this might be a very powerful tool for helping to build better quantum computers, I'm going to let you. I'm going to talk a little bit about how we control how we build these computers, how we control these quantum bits. So you see, these qubits usually, they're described by these superpositions, and in order to perform these gate operations on them, in order to rotate the qubit on these spheres, we need to send analog signals to these qubits. Okay, so usually these would be microwave pulses or laser pulses on the actual physical qubits. So the qubits will sit in some array of qubits. This is the quantum processor. And then we shoot at the qubits this orchestra of microwave pulses. Okay? And also we get back some pulses. It's like we're playing little notes to the qubits. And then we're also getting back some signals back from the quantum processor. And this is all analog signals. And you can just think about how much information we need in order to describe all these pulses that we use to control qubits. So people are now starting to think how neural networks might help us identify the patterns in the pulses coming back from the quantum processor, and maybe help us generate the right sort of parameterizations of the pulses that we need to send to the qubits, and also allow us to measure signals that come back from the quantum processor, identify the patterns and the correlations that we want to identify in order to make real-time decisions on what would be the next pulses to send back to the quantum processors. Actually, at QM, at Quantum Machines, where I work, we develop systems, all the classical systems, both hardware and software, that interface the quantum processor, okay, interface the quantum system. So the systems we develop allow quantum developers to write their algorithms, their quantum algorithms, in a quantum computing language, our quantum computing language, which then is translated through our software layers and then our hardware to the physical pulses, these analog signals that go into the qubits and operate the quantum processor. Again, with a lot of importance for real-time feedback between the control hardware and the quantum processor itself. And we're just starting to explore these days how neural networks might help us optimizing the control operations on these qubits and optimizing these feedback loops. So with that, I'll thank you. And if you want to get any more information, you're welcome to contact us.